Hi everyone. So in the third unit, we have studied what are all the memory allocation methods like demand paging, segmentations, everything we have studied. And in the fourth unit, we are going to study the mass storage systems. Let us have a discussion. Let us have the startup discussion with their objectives. So the main objective is to describe the physical structure of the secondary storage devices and its effects on that particular device usage. The second objective is to evaluate the disk scheduling algorithm. And third one is studying about the RAID, which gives the services provided for mass storage. Yeah, we have already discussed the basics of storage systems in the first unit itself. Let us discuss the basics of disk structure. Say for example, if you are having a hard disk, it consists of different components, which is illustrated in this slide. This slide will explain the moving head disk mechanism. So this hard disk actually it consists of different components. Say for example, a spindle is there at this center of this hard disk, and it consists of several platas, or we can call it as a magnetic disks. So this is actually a number of platas are there in this hard disk. The whole thing we can call it as a cylinder. Number of cylinders are there actually in this hard disk. So track means which is actually a circular portion of a particular cylinder or a particular disk, magnetic disk. So say for example, if you are considering a sector, sector is nothing but a particular portion of a particular track. We can call it as a sector, and this is called actually arm assembly. Arm assembly which holds the read write head. This read write head is used to access the data which is present in the magnetic disk. Say for example, if I want to access data, say for example I want to read or write data in this particular track. So with the help of this arm read write head, I have to access this particular track for the purpose of read or write any data in that particular track. So we have studied the basic components of the disk, magnetic disk. So we are now going to see the overview of mass storage structure. Actually, a magnetic disk, this provides a bulk storage, secondary storage of the modern computers nowadays. What we have been actually working on, the laptops, the desktops, which consists of hard disks, which provides a bulk of secondary storage. So this hard disk, the drives which is present in this modern computers rotates from the speed of 60 to 250 times per second. This is the rotational speed actually for average rotational speed of a traditional hard disk. So the transfer rate of the disk is actually called as a rate at which the data flow between the drive and the computer. So we have to see another factor called a positioning time or a random access time, or we can call it as a seek time also. So this is the time, we can call it as a time to move a disk arm, what we have seen in the previous slide, to a desired cylinder, a particular disk or a particular cylinder in that particular hard disk. So this is called actually a random access time or positioning time or a seek time. And then the third factor is actually a rotational latency. So here it is the time, the rotational latency is actually a time for a desired sector to rotate under the disk. So here sector is actually rotating under the disk head. So this is actually called as a rotational latency to find a particular track in a particular sector. So the final factor is actually a head crash, which is actually a bad thing if it happens. This results from the disk head making contact with the disk surface. So these are all the factors we have to keep it in your mind before entering into the further portion of the syllabus in this unit, mass storage structure. So so what we have studied is actually magnetic disk, which is present in this traditional computer or the laptops, which provides a bulk of secondary storage in the modern computers of the modern computers. So this kind of hard disk is actually a drive which rotates at 60 to 250 times per second. So we have seen the first factor called the transfer rate, which is the rate at which the data flow between the drive and the computer, and then the random access time or a positioning a time or a seek time, which is a very important thing. It is actually the time to move the disk arm to the particular very specific desired cylinder. So this is called actually seek time. Seeking a particular track in a particular specific cylinder is called actually a seek time. So this is the time to move a disk to disk arm to a desired cylinder. And then the third factor is actually rotational latency, where actually your desired sector is actually rotating. So that time for a desired sector to rotate under the disk head is called actually rotational latency. The final thing is head crash, which is actually a very bad thing. If this happens, it results from the disk head making contact with the disk surface. So the next thing, very important component is actually host controller and the disk controller, where we have to understand what is actually the host and the disk controller before entering into the further portion of the syllabus. So input output bus, which is responsible for communicating the drives, the disk, for writing or reading out the data from the disk. So the host controller is at the computer end. So computer end, we are having the host controller. So and the disk controller is built into the disk itself. So this is very important. Disk controller, which is built into the disk itself. Host controller is not as a part of the disk, which is present at the computer end of the input output bus. So say for example a system or a processor, say for example a CPU issues a command to the host controller via input output ports. The data is actually transferred between the magnetic surface and onboard cache by the disk controller. So from the magnetic disk, the data has been transferred to the cache, which is actually called as an onboard cache by the disk controller. Then actually from the cache, the data is transferred from that cache to the host controller. So this is actually happening with the help of actually input output bus. So as I said earlier, this two component is a very important thing, host and disk controller. Host controller is the computer end of the input output bus. Disk controller is actually a controller which is built into the disk itself. So this, say for example, if a CPU issues the commands to the host controller via input output ports, the data is transferred between the magnetic disk disk or the magnetic surface and towards the onboard cache. So there will be a cache between the disk and the host controller. So then the data is transferred from the cache to the host controller and the motherboard memory at electronics speed. So hard disks. The next topic is actually hard disks. So this is actually a generic thing where everyone should know the basic thing about the hard disks. So the platters, what we have seen in the first slide, is actually ranges from 0.85 inches to 14 inches. So this is actually a conventional information. Commonly it is actually 3.5 inches, 2.5 inches and 1.8 inches. And this thing is very important, where we are going to discuss in the further slides also. So sector 0, what is mean by sector 0? It is actually the first sector of the first track and the outermost cylinder. Say for example, this is the spindle and this is actually a cylinder. Say for example, in this cylinder, what we can call it as a sector 0 is, so this is the first sector in the of the first track of the cylinder. Say for example, what is mean by sector? Sector is nothing but the circular portion of the cylinder. So the circular portion, which is nothing but the outermost circular portion, we can call it as a first sector of the first track on the outermost cylinder. So then when we coming to the memory, so it is actually the secondary memory, the 30 GB to 3 TB per drive we can store. And the performance, while considering the performance of this disk, the transfer rate is actually theoretically it is actually 6 GB per second, gigabits per second. But effective transfer rate is actually, that is the real transfer rate, is actually 1 gigabits per second. I think no one see this kind of transfer rate. So the real transfer rate might be 1 gigabytes per second. The seek time may be from 3 milliseconds to 12 milliseconds. Normally it is actually 9 milliseconds common for a desktop drives. So this is actually rotational speed of the spindle they have given, and for that particular rotational speed of spindle they have given the average latency. So the first commercial disk drive is shown in this slide. This is actually an IBM system, IBM RAM DAC computer, which includes IBM model of 350 disk storage system, which has been developed on 1956. This consists of 5 MB of this can store a 5 MB of data, a 7-bit character data. The platters, what we have seen is actually here with 50 platters are there. And the size of the platters, it is actually 24 inches of size. So consists of 50 platters. Maybe this is the thing. So for this kind of for this IBM disk storage system, the access time is actually less than 1 second. So coming to the disk structure, as I said earlier, sector 0 is a very important factor. It is actually the first sector. Sector 0 is actually the first sector of the first track on the outermost cylinder. So mapping, while I'm going to write or read a data on that particular sector, the mapping proceeds in order through that track. First it initially identify the track, then the rest of the tracks in that cylinders, everything it will it will check each and every track in that particular cylinder, and then through the rest of the cylinders, each and every cylinders in the disk, it have to check from the outermost towards the innermost. From the outermost, this is, I say for example, this is the cylinder, from the outermost towards the innermost. Okay, so let us discuss what is mean by disk scheduling. So this is a very important question and very important concept while we considering the mass storage system. The operating system is responsible for using the hardware efficiently. So as I said earlier, from the first unit, we have to use everything in a efficient way. So the hardware should be used in this. Hardware here we can consider as a disk. So we have to use that hardware hardware in an efficient way. For the disk drives, this means having the fast, while considering the disk drives. So here in this fourth unit, we are concentrating on the disk drives. So what may be the hardware efficiency, we can call it as, this means that having the fast access time and disk bandwidth. So these two factors, performance factors are to be considered while considering the disk drives. The fast access time should be there and large disk bandwidth should be there. So for a magnetic disk, the access time has two major components. So what are all the two major components we can see? The first one is seek time, and the second one is rotational latency. So seek time, as I said earlier, we have studied, is the time for the disk arm to move the heads to the cylinder containing the desired sector. Rotational latency we have studied already, is the additional time for the disk to rotate the desired sector to the disk head, to track that desired sector during their rotation on the disk head. So disk bandwidth is the total number of bytes transferred, how many bits you are going to write, or how many bytes you are going to read. So that is the thing, total number of bytes transferred divided by the total time between the first request. Say for example, it is actually the time difference between the first request for the service and the completion of the last transfer. So that is the definition for disk bandwidth, which is actually the total number of bytes transferred divided by the total time between the first request of the service and the completion of the last transfer. So we have to maintain this thing, that is the minimum seek time to search a particular sector in the cylinders. So we have to have a minimized seek time. Seek time should it might be an approximate value of the seek distance also. So we will see this thing in the coming slide. Okay, fine. So disk scheduling. So there are many sources of disk input output request. Say for example, I want to save a file in a particular hard disk in a particular folder means, so that is also an input output request. So we can consider that scenario as a user process. So if a user want to save some file or save a data in that a particular hard disk means, that is called actually user processes of input output request. Say for example, if a system, say for example a program is actually running, it want to read a data from the disk, then that is called actually system processes. OS will also do the same thing. So there are many sources of a disk input output request. Say for example, it is from the OS, system processes, or from the user processes also. So input output request includes, what are all the input output request includes. So first thing is input or output mode, whether I have to write something on the disk, or we have to I have to read out from the disk. And then second thing, that is actually the mode. So second thing is actually disk address, where I am going to write or read operations. So the third one is actually the memory address. So the fourth one is actually number of sectors to transfer. So these are all the important factors that have to be considered in the input output request. So then the OS maintains a queue of requests. So this request has to be maintained by the OS as a queue of requests per disk or per device. So ideal disk, if you are considering an ideal disk, then it can immediately work on this input output request. So based upon, say for example, if the input output request from the OS, or it may be from the system process, or it may be from the user processes, anything it arises. So if the disk is actually an ideal, it can immediately work on the input output request. So say for example, if a disk is actually a very busy in manner, then it means work must be in a queue. Actually we have to put the input output request in a queue. So input output request in a queue if the disk is actually busy. So we are having a number of optimization algorithms that have to be studied in the further slides, that only make sense when there is a queue for the input output request. Okay. So let us continue with the disk scheduling algorithms. So from this slide we can illustrate the different kinds of disk scheduling algorithms with this example. So say for example, as I said earlier, the device controller and the host controller is a very important component in the in communicating the in communicating the disks and the CPU. So the drive controllers have the small buffers. Yeah, definitely it consists of small buffers where the input output request queue is being actually filled and can manage a queue of input output requests. So it consists of the disk drive where the drive controllers is actually present. As I said earlier, it is present in the disk itself and have the small buffers and can manage a queue of input output request. So several algorithms exist to schedule the servicing of a disk input output request. So in this buffer, this input output request is actually getting filled, and this have to be served in with the help of several scheduling algorithms. So let us illustrate with this example the different scheduling algorithms. Say for example, it consists of 0 to 199 ranges of request queue, where actually the current state of the head pointer points the 53rd sector. So the request queue consists of this data. The first data is actually 98, 183, 37, 122, 14, 124, 65 and 67. So this is actually the input output request queue, which consists of this data. So let us start with the first algorithm, which is called actually first come first serve. So the queue, as I said earlier, it consists of this data. So it has to search. It has to search the first thing is it has to search the 98th sector, but actually the head points at 53rd sector. So here they have been actually mentioning the 53rd sector. So this is actually where the head initially points out. And in the first come first serve algorithm, what it does actually is, what are all the inputs that arise first, it has to be serviced. So here in this input queue, what is the next next request have to be serviced is 98th sector. So from the 53rd, it just seek, or it first search the 98th sector, and then the second thing what we have arrived in the queue is 183rd. So from the 98 it will search the 183rd sector, and then from that 183rd it will search the 37. So this is the third third input output request that has been arrived. So from 183 it has to search for 37. From 37 it has to search for 122, and from 122 it has to search for 14. So from 14 it has to search for 124. So from 124 it has to search for 65, and from 65 it has to search for 67. So this is how it works, the first come first serve scheduling algorithm. So this is say for example, this is the input output request queue, which consists of 98. So initially the head points out the 53. So what are all the input output request comes, so it has to be served first. So the second algorithm is shortest seek time first, which selects the request with the minimum seek time from the current head position. This is a very simple algorithm. It selects the request. So say for example, this is the request what we have considered so far in this scheduling algorithm. So it will first select the request with the minimum seek time. So how to find the minimum seek time? Let us I will explain you. The SST of scheduling is a form of SJF, a shortest job first scheduling algorithm, may cause a starvation. So starvation, how it will cause a starvation, I will explain you. So initially how it works, the shortest seek time first, how it works. So initially the head points the 53rd sector. So this is actually the queue. So while considering this queue, let us have the smallest, sector from where the 53rd it has to reach. We have to check. So from the 53rd sector, the shortest job is actually among this, input output request queue, input output request queue. So 65th is actually the 65th sector is actually easy to access, easy to seek or easy to access, and hence initially from the 53rd it will first reach the 65th sector, and from the 65th it has to reach the 67. So after 65, so this is the next highest range of sector, so 67. So this is actually 67. So this is actually after 67 it has to reach the 37. So 37. So for this is the minimum seek time. For this is the minimum seek time. So and after that, what will be the minimum seek time? We can identify, and we can go for that particular sector. And from 37, so what for if I am seeking for another sector, what will be the minimum seek time? So from 37 maybe 14. So 14, and from 14 it has to reach 98, and from 98 it has to reach 122, 124, and finally 183. So the next algorithm is actually scan. The disk arm starts at one end of the disk. So first it will starts, the disk arm starts, the header starts at one end of the disk, and then move towards the other end, servicing the request. So from the one end it will move to the other end, servicing the request, and until it gets to the other end of the disk. So until it gets to the other end of the disk, the head movement is reversed. So this is called actually reversed, and servicing continues. So from the one end of the disk it will go to the other end, and the service is actually reversed. The scan algorithm, sometimes called as an elevator algorithm, but note that if requests are uniformly dense, largest density at the other end disk, and those wait the longest. So in the previous as I said in the previous slide, we consider the same same scenario. So queue are having this data. So initially the head points out the 53rd one. So how it works actually, so it will go towards the one end of the disk. So from the 53rd it will go to the 37th sector, and then 37 to 14. So with this queue it will reach the 14, and finally the one end of the disk. From the one end of the disk it has to be reversed. So from the 0, what it has to search, so 14 we have completed, 37 we have completed. So after that what I have to reach is 65. Yeah, 65 is here, and then I have to reach 67, and then I have to reach 98, and then I have to reach 122, and then 124, finally 183. So the next algorithm is actually C-scan, circular scan, otherwise called as a circular scans. It provides a more uniform wait times than the conventional scan method. The head moves from the end of the disk to the other, servicing the request as it goes. So similar to the scan, but it is actually a circular scan. When it reaches the other end, however, it immediately returns to the beginning of the disk without servicing any request on the return trip. So in case of the previous method, that is actually the scan, this is the starting of the cylinder, or starting of the disk, and it will do a service for the input output request at the end of the cylinder, and it goes reverse, servicing the remaining thing. But in case of C scan, it will first service the forward in the forward directions, and again it goes without any servicing, and from here it starts servicing the input output request. So this is actually C scan. This treats the cylinders as a circular list, as I said earlier, that wraps around from the last cylinder to the first one. Let us have the example, same example. The queue is actually the same queue, and head starts with the 53rd. The next sector it has to search is 65. Then the next sector is a 67, 98, 122, 124, and 183, and it will come to the end of the disk, and from this end of the disk it will not service at the return. It will not service at the return. I mean, it will not search any sector while returning towards the initial point of the disk. So it will not service anything. It will not service any input output request during the reversing process. And at the start of, again from the start of the disk, it will again do the service of input output request for the 14th sector and then for the final 37th sector. So finally, C look. This look a version of a scan, C look a version of the C scan also. So ARM only goes as far as the last request in the direction. So in the previous method, we will go at from the starting of the cylinder, disk, towards the end of the cylinder. But in case of C look, it only goes as far as the last request. Say for example, if the request is here, it will not go to the end of the cylinder. It will only goes to the last request. So then reverses to the directions immediately without first going all the way to the end of the disk, as I said earlier. So same example, it's the same queue, and head starts with the 53rd one. So the next sector it has to search is the, next input output request is 65, next input output request is 67. So same thing, 98, 122, 120, 124, 183, and it will not go to the 199th 199th sector, which is actually the last end of the sector. So again it will goes return without any servicing. Say for example, it won't service the 37th one. It will go return reverse towards the 14th sector, not the initial point of the point of the cylinder. So this is actually the 0th sector. So initial point of the cylinder, it won't go in case of the C look. So as in the previous case, it will go to the end of the cylinder. So either at the last end and also at the initial point of the cylinder also. So it will go to the during the reverse, it will go to the 14th sector, and then it will do the service for the 37th thing. So selecting a disk scheduling algorithm is another important task. So we can consider SSTF, shortest seek time first, is a common and has a natural appeal. So this will be the most common thing where each and every traditional conventional system is actually using. Scan and C-scan is a perform better for systems that place a heavy load on the disk. So it consists of a less starvations while we compare to the SSTF. When we are having the SSTF, it will first search the from a particular input output request, or from a particular a sector, it will reach another sector. Say for example, this is A and this is B. It will reach this B sector, which is having a minimum seek time. So from this, what I am searching is what is the shortest seek time I have to search. So this is the concept in SSTF. So say for example, every time if an input output request is coming with a shortest seek time, so some sectors, say for example X, it will not get serviced since it consists of, it has a very long seek time. So that is actually starvation they are actually considering here in the SSTF. So while we comparing the SSTF, scan and C-scan will give a less starvations. Performance dependence on the number and types of requests. So this scheduling algorithm should return as a separate module of the operating systems, allowing it to be replaced with a different algorithm if necessary. Either SSTF or look is a reasonable, as I said, SSTF and look is actually a reasonable choice for the default algorithm. So whatever the rotational latency, it is actually a very difficult task for the device to calculate. So this is the thing we have to concentrate. If any question asked in disk scheduling algorithm, so you have to write all the algorithms. If they are mentioning any two algorithms, any three algorithms, you have to write any two or any three algorithms, any four algorithms. So it is actually a very important thing. So if a disk is actually an ideal thing, so it will do the input output request immediately. So if the disk is actually busy, so a disk controller will have a buffer and input output request will be stored in that buffer, and from that disk controller, this input output request is being serviced. For servicing, we are having a different disk scheduling algorithms. So we have seen one by one from last some previous some 6 to 7 slides. So so that's all about the disk scheduling algorithm.